set union, etc.
All right. Hi everyone, and thank Mike for the introductions. Yeah, I was actually his student 5 years ago. All right. So my talk today about private set union, and it's focused on parallel computation for the large number of parties. And this is a joint work with two of my students, Joy here and Sơn, and Marina from University of Buffalo. All right, so here is the outline of my talks. I want to have a quick introduction about what is PSU and its applications, and then have some history about PSU, what people are working on right now, and then the talk of today focus on multi-party setting with some performance and then open problems. All right, so you heard about PSI, right? You understand what PSI is, and PSU is very similar, right? Except the U and the I here. So you here, you want to compute unions, yeah. So let's say in you have one party have the sender with PSU, receiver with the MPC. The output will be MPCSU, right? And then you remove the P. P appear twice, so you output only one times here. So in some sense, PSU want to hide the intersection items. It, unlike PSI, where you want to compute it, now you want to hide it. All right, so with that functionality, what is the applications? So when you think about application, you might think like some scenario where you want to remove duplication, right? So IP blacklist computation is one of them. Each party have a list of IP blacklist, and they want to compute the unions. So what they want to hide here, they don't want to show who have the first IP, right? And they want to hide how many parties have it. So PSU can be used for private database queries. Clearly, the full join of two tables. They can be used in network monitoring, like graph computation, and some other application like machine learning stuff. All right. So you have the good overview about PSU's application, and now I raise a questions. I'm not sure if we can answer it. So yeah, I'm working on PSI before, so that's why I want to say, hey, what is the relationship between PSI and PSUs? Or they are a sector, younger, older, or a string? So how we can answer these questions? Any idea here? No? Yeah, in my sense, for me, when I try to answer this question, I want to see how many people working on PSI and how many people working on PSUs. Like my sector, my older sector, they have more toys than me. So it means, yeah, so you can see it, right? I brought out this slide from Peter Rindo here, like about 10 years ago, when I'm first starting working on PSI. And at that time, still have some papers. You can see here, right? And it have the name of the author, but maybe the light, you can see it. But right now, after 10 years, you can see, for me, like right now, they have too many papers. I don't know what is state of the art right now. So that's why we have another 2 talks later, like the previous one and another 2 later, we'll mention about PSI. So what I can do, I do a Google Scholar. I search for PSIs. For 10 years, you can see like here, maybe barely to see, but around 5,000 results about PSI. Yeah, it's not only about like, it not mean like, hey, they have 5,000 papers, but it's more about 5,000 papers mention PSI in their paper, right? All right, now looking back to my question before, how about PSI use? So I'm looking on that one with my here in around 6 years ago. Like we have the ACE-script paper on that time. And then from that time, a few papers working on it. But to be honest, it's still countable, right? Yeah, and I'm not sure what is the next 10 years. Maybe people here will examine it, and maybe they have too many papers. Anyway, come back to what I want to say today about PSUs. So they have several work on two-party setting, but not many work on multiple-party setting. Yeah. And I have a good picture here about state of the art in two-party. Let's say I use 1 million items with very slow network. The state of the art right now is still under 1 minute. It's not that good at PSI, but still, like, so in some sense, still practical. And for multiple party setting, I use like 16 times slower, right? That's the number of set size here with 4 parties, faster network. But you see still here like 5 minutes. So in other words, there is a big gap between multiple party and two-party setting. Yeah. And yeah, I know some of you here can raise the question, how we can bring the gap between two-party and multiple party, right? To answer these questions, we can go to another question. How to extend the fastest two-party protocol to multiple party protocol? Yeah. So a little bit, come back to PSI. In PSI, if you have the fastest two-party protocol, you can plug in multiple party setting. And then you can get efficient multiple party protocol. But it's still not the case in two-party. And I will show you why. Yeah, before going to that, I want to have some literature reviews on two-party and multiple party. So the state of the art in two parties, they use PMT, reverse private membership, or they use sub-for-based protocol. For multiple parties, they have different techniques, and of course, they can use for two parties, right? And the state of the art right now, they use secret share, PMT, OT, several combinations. I will go to, my talk today will jump to this approach. Yeah. All right. What next I have? All right. So, yeah, I don't remember the slides. So before going into two-party, multiple party, I just have a very hint here about what we want to compute. What is the functionality for multiple parties? Again, like we have several parties, they want to compute the union only, right? So the main challenge here is, if we use two parties PSUs, the question here is who sent the union item to the receiver? In PSI, every people have the same item, so it should be fine, right? In PSU, you want to hide who have X. And also you want to hide how many parties have X, right? And a very common setting when you deal with multiple party setting here is a few party collude. You don't want to reveal additional information. Yeah. All right. So again, to see how you can do two-party to multiple party, I want to have very quick review on two-party setting right now, how people doing it. Very, very naive idea is that you only send, like I'm the sender, I'm only send the item to you if you don't have that item, right? So this is the key point for union. And how they can do it, they have reserve PMT, where this guy have the X and like one item, the set, and another sender have only one item. And you want to give the bit indicate whether Y belong to X or not, right? Yeah, in that case, you have number 2, then you get the bit B equal to 1 because Y belong to X. And then you use subsequent OTs. You put number 2 and some random thing, some garbage thing, and then you only send number 2 to this guy if B equal to 0, right? But in this case, B equal to 1, so that's why the receiver receive nothing. Yeah. So the receiver can output the unions 1, 2, 3, and you see here, the receiver never know whether the sender have number 1 or number 2 or number 3. Right. So in some sense, you can see PSU, you want to hide the intersection items. Yeah. All right. So the same scenario for number 4 here. Let's say number 4, you receive a bit b equal to 0 because y not belong to x, right? And you book.
This is revealed to the receiver? Isn't that already too much information?
I'm sorry.
The b equals 0 or b equals 1?
Yeah, but you can simulate it from the output, right? So let's say, yeah, this is a very good question. So let's say I have 4 and 1, 2, 3. From the output, I will have 1, 2, 3, 4. Right?
For everything, don't you so you assume that you learn the size of the other party's size?
Yeah, you learn the size, yes. Yeah, I'm sorry. So in that case, I only do a PSU for one item. So that's why assume that you need to learn the size of the, like in PSI and PSU, we assume to learn the size of the party. And if you don't want if you want to hide it, probably you have to put the same value or some, like, I don't know. Yeah.
So can you comment a little bit about the efficiency parameters based on the size of the inputs, because PSU is just complement of PSI, right?
Yes.
So there must be some efficiency considerations that makes PSU different from PSI.
Yeah, I will.
There's no difference between them.
Your answer can be, your question can be answered by the end of my slides. Yeah, but right now I can tell you a little bit. Right now, because the specific thing in PSU, you want to hide, you have to send all the information, right? Like when you learn about like in information theory, if you want to compute the intersection, you only send the intersection item. But for PSU, you have to send the entire set somehow, or maybe you have to send the set difference. So they have some.
How are the inputs represented? If the inputs are represented as a bit vector or that way?
Oh, the value here, a bit vector. It can be the bit vector. Yeah. So right now, the efficiency of multiple party PSU have to be n times n square times n. Yeah. Maybe you can see the table later. Yeah. All right. But I think the problem here in PSU, you can see like here, right? 1, 2, 3, 4. You can see like, hey, the b should be 0 or 1. Yeah. So that's why it's okay to lick the bit indicate whether y belongs to x or not in these scenarios. It's not the case in multiple party, but it's the case in 2 parties. All right. So let's say I think I have 10 minutes, right? Oh, no. All right. So let's say I have how to use 2-party protocol for multiple parties. If we just repick X1 between P1 with P2, I learn number 3. Yeah, it's very naive solution, so I can go very quick here. If I run P1 with P2, then I learn number 3. If I run P1 with P3, I learn number 3 and 4. I can compute the union, right? But again, it leaks the information, hey, number 3 appear in P2 and P3. Yeah. So we need a little bit clever ways how to use 2-party to multiple party. So the key idea we can do it is that we follow this equation. Let me use the mouse here. We follow these equations. First, you want to keep X1. And the second one here is you want to remove duplication. Every item belongs to X1, you want to remove it, right? And you keep the difference between X2 and X1. Yeah. And you keep the same thing for X3. You remove duplication, you remove everything appearing in X1 and X2. Yeah, how you can do the unions. So go back to similar to previous slide. Now I use 2-party PSU between P1 and P2. I get number 3. And to follow these equations, I have to use the same result that what I get here, move to here, right? And now I get only number 4. Yeah. And again, P1 can see, hey, when he received 3, when he received 4. So how we can address this problem? We introduce 2 building blocks. The first one is about membership of liver transfers. And the second one is very interesting right now, is about oblivious shuffle and decryption. Yeah. All right. So come back to the, so that's why you can see like X1 still maintain had encryption of 1 and encryption of 2, right? we want to put everything under encryption because we don't want to review which party have it and how many party have the value. For number 2 here, for the P2 here, because number 2 appeared in X1, right? So that's why you have encryption of some garbage thing and number 3. Yeah. So on and so forth, you have number 4, you have encryption of garbage and garbage because 3 appear in X2 and 4 appear in X3, right? So now you are on the good shape. Now you have it's a set of encryptions. The only thing you need to do here is you search for it, you review it in the random order. Yeah.
Can I ask a question?
Sure.
For PSU, for 2 parties or multiple parties, the way that I understood it is that your protocols are inherently sequential, right? So can you comment on what is the number of rounds if one person has L elements?
I have that question in my next slide. All right, sorry about that. Let me finish this framework first. So you have a very high-level idea about what multi-party PSU work. They need to do secret share and private membership. They need to do magic modification to have the fact, to get the fact of the real unions, and then you subfolding it, right? Okay. So in my talk today, I only focus on public key operation. It's not because I don't like it. It's not because I don't like symmetric key base, but it's because right now the communication is very not efficient. It's due to the subfolding protocol. Yeah, so my talk only focus on public key based protocol, and here is the slide that you want, right? So I think like multi-party PSU is not very, like not many people study on it. And my paper last year, we have everything in ON, it's not good, right? And then this Unix paper reduced the pairwise secret share private membership using some batching technique. And the paper I present today, we somehow can reduce the row complexity, everything in O1, except the subfolding. Yeah. Because the main important thing in multi-party PSU is that you want to hide who many parties have it, how many parties have one item, right? And you want to hide the shorts, like which party have X as well. So you have to do subfolding. I'm not sure how to prevent it right now, but this is the state of the art. You need ON subfold for a row for the subfold. Yeah.
What is the dependence on the universe size?
I'm sorry?
What is the dependence on the size of the universe?
So you mean the length of the items?
Universe, like from which the elements are going
yeah, right now people, like for experiments, right now people use 64 or 128-bit.
you are treating that as a constant?
Yeah.
64-bit and 128-bit?
Yes, constant, yeah. For PSI, you can do like, this is a good question when we get from reviewers. So in PSI, right, you can hash, if you have very big, very long vector, you can hash it, and you can compute the intersection, and you can review it in the index, right? But in PSU, you have to go together with it. Because you want to compute the union, you not compute the intersection. So right now, people working on, with my paper, I think we can do for upper 3. Yeah, it's just like, or maybe another idea here, you chunk by chunk, right? You have a long big vector, you just chunk it. Anyway, so this is state of the art right now. I think I'm running out of time. All right, so this is what I want to go for the paper. I'm not sure how many time I have. All right, 10 minutes. Yeah, all right, thank you. I have barely 10 slides. So, all right. So the membership OT, like the name say everything, right? The sender have Y, the receiver have X. You want to send M0 or M1, depend on whether Y belong to X or not. Yeah. So you can think about membership OT is the variant of OT for sure. And you can use membership OT for the 2-party setting. Yeah. For multiple parties, you use membership OT to send the encryption of Trieu or encryption of fact items. Yeah. All right, so I'll go very quick on the how we do with implementation of membership OT. So back to the question that you raised here. Now, instead of review the bit, we have to do secret sharing because it's a multi-party setting. And depend on BS here, you just flipping M0 and M1 and get MB at what you want to do. Yeah, I just believe on me on this one. I just give it. All right. So go back to the main idea, how we can reduce the magic modification to all one row. So it looks like that you cannot prevent, right? It looks like that you cannot prevent step by step. You cannot prevent, hey, you from this one, you have to yield the result here to the next one. Yeah. And we can prevent it by some, like clearly that we need to prepare some random messages, right? And instead of using the encryption of some default value, now you use the encryption with a randomness. Yeah. And we use additive homomorphic encryption to support the computation. Yeah. All right, let me move on. So how we can, let's say in this sample, I gave you the goal is you want to compute the fact or the real encryption of the thing. It belongs to X3, X4, but it not belong to any other parties. Yeah. So the protocol works as follows. P4 and P1 run MOT. He have, let's say we have number 4 first. You have number 4, you prepare for a pair for the OT. First the encryption of 0 and another encryption of randoms. And because 4 doesn't belong to X1, you have encryption of 0. You do the same thing for P2. And the key point is that because 4 belongs to X3, right? So that's why you get encryption of random. And with additive homomorphic encryption, you get encryption of 0 here. You re-randomize it, send it back to P4. P4 has encryption of 0 here. Compute like he add in this guy, this guy, this guy together. And because this randomness, when he add with his encryption of 4, it gave you some garbage thing. Yeah. So this is the key idea. In the paper, we have something, but it is the key idea how you can make it like in all one row. All the MOT can be run in parallel. Yeah. All right. Let's say for number 5, because 5 doesn't appear in any other party, so you will get encryption of 0, right? And when you add up with encryption of 5, you get whatever you want to keep here. So with that high-level idea, you can get all one row complexity. For decryptions, when you collect all the data, you want to decrypt it, right? So the functionality that I want here is you have the set of cybertext. Each party have the permutation because you don't want to show who have the items. Each party have the key of the encryption scheme. And I don't know why, but in previous work, they combine the subfolding and encryption together. Yeah. So in our work, we realize, hey, why not you just separate them? The subfold is very cheap, right? The subfold you just send, re-randomize, and send it to another party. So the subfold is very cheap, so you can do it in the like very fast. And you can prepare some encryption of 0. And for decryption, you can do in parallel. Yeah. So that's why the key high-level idea how you can get all one for decryption and the subfold still have to be doing in sequence. Questions? Nope.
Can I ask a question? So you are using an additive homomorphic encryption scheme, right?
Yes.
And then later on you need to decrypt it.
Yeah.
So the values will keep adding up. So if you use something like algorithm encryption, you need to be able to decrypt it in the exponent. So what type of encryption scheme do you use?
We use algorithm here. We use algorithm encryption scheme here.
Yes, but you need
you
to
add with 0. The point here is that, yeah, the point here, very good point here that you add with 0. For the real idea, this is what I want to get back, right? I add with 0.
Oh, I see.
Yeah, for the random, I don't really care. Whatever you want to do, right? Yeah. Questions? All right, here a performance of what we have. Like we have around 2 to 4 times improved, depend on the number of parties. Working with many parties, then the element is more. Right now, it's only working on. I think it's only efficient on like this number of parties. This number of items. All right. So looking back to what we have, so this is the big picture of our protocol. Follow this this equation, have some encryption of like a random or encryption of what you want to get, and the 0 here indicates the real value, right? And then you can do a permutation with some preparation for encryption of 0 and do a parallel decryption. Yeah. This is a summary that what I mentioned with you earlier. So go to the open problems. I think it's still a chunk of problem for multiple party PSU or even for 2-party PSUs. So what I present today only on public key based protocol, right? And right now, multi-party PSI, PSI, not PSU, the state of the art still is based on symmetric key. So how we can improve, how we can have efficient symmetric key based protocol for multiple party PSU. And also how we can reduce the row complexity from O(n) to O(1). It's not like my trick, it's just like a mess of several steps. And then another question here, they have no surprise, right? They have no malicious protocol on multiple party PSUs. In 2-party, they have a few papers, but it's still not practical for now. And another extension like PSI, when people looking on fuzzy circuit threshold or symmetric, whatever there, we can ask the same question here for PSU. All right, this is all for my talk. Yeah, thank you. Any other questions?
Can I ask you a question?
Sure.
So it seems you are sticking to the sequential setting. If
Yeah.
you have the setting where everybody talks to one party, how does it compare? Because they must be very fast, right?
Yeah, so you asking like you have this assumption where you have one server or?
Yeah, let's say you do some brownfield
Actually my group with my student, we're working on balloon filter base. A balloon filter have a problem like in PSI, maybe you know the intersection. Then you have the balloon filter, you can check, right? You can get the items. But in PSU, you have to get the item from the filters. So it's tricky with PSI and PSU. But back to your question, I don't know, I don't realize any paper based on like have the server 8 PSU. I don't realize any paper about that one. So maybe you can write some. It seems to me, I don't know if for server setting, still you have to hide the items. Yeah, when you send, if the server see it, then hey, you know who you have the items, right? So in some sense.
You can use added-diffeomorphic encryption.
I'm sorry?
You can use added-diffeomorphic encryption.
Yes, yeah, probably, yeah. All right. Is there any other questions? Yeah, but with my student, we somehow make balloon filter work. At least for 2-party right now, but not sure about multiple party.
Okay, let's thank the speakers again.
Thank you.
Give a quick break for now, and then we'll reconvene in 45 minutes.